first popular seminar of the year, and those of you who are new to the Popper seminar. This is always held on a Tuesday afternoon, and in fact it's been held on a Tuesday afternoon since around 1946 when Karl Popper first arrived here. We were at different locations in an old building. We've since moved to the Lakatos building, so ironically the Popper seminar is in the Lakatos building. And but it is really the continuous descendant of Popper's original seminar. Now he's gone, it was just called the seminar back then, right? It's like French fries in France. And we're very pleased today to have Owen Griffiths with us. He was previously a lecturer in fellow at St. John's College at Cambridge. He's with us all year leading our logic courses here at LSE. And he's going to speak to us today, I assume, about the nature of logic, isomorphism, invariance, and overgeneration. Owen?
Thank you very much. Yeah, thank you for the invitation, and thanks everyone for coming. Although, frankly, with a title like that, how could you not? So, what I'm going to be talking about today is the nature of logic. So, I'm going to be looking at a particular account of what makes, what's distinctive about logic, what distinguishes logical concepts from non-logical concepts. An account given by isomorphism invariance. I'm going to briefly defend that, and then I'm going to look at the main problem that comes up with that sort of account, the overgeneration problem, and try and explain it away and say that there's not really any such problem for this account. It's all going to be, I'm going to try and keep technicalities to a minimum, so there's going to be a little bit at the beginning when I explain the account, but by and large this should be reasonably accessible, I hope. So, here's the plan. Start by motivating isomorphism invariance by the thought that logic is distinctively formal. Then give you a brief statement of the account, look at the overgeneration argument, and then try to refute a few different versions of it. So let's start, as everyone should, with a quote from Timothy Smiley. And here's what Smiley says about the nature of logic and logical consequence. The idea of a proposition's following from others, and they're implying it, is central to argument. It is, however, an idea that comes with a history attached, and those who blithely appeal to an intuitive or pre-theoretic idea of consequence are likely to have got hold of just one strand in a string of diverse theories. There's this thought that if we appeal to some well-behaved, intuitive, pre-theoretic notion of logical consequence or validity, we're going to go wrong because it's a bit of a tangle of ideas, the history of writing about validity. And I think that's exactly correct. In fact, I think the following ideas at least are going on when we look at what people have had to say about consequence or validity. The major thoughts that seem to be in the literature are that it's distinctively modal, so there's a component of necessity to logical consequence, and that's of course the sort of thing we teach our students when we start doing logic. We say, well, you know, an argument's valid if it's impossible for the premises to be true and the conclusion false. So we've got this strong modal thought going on. And also a thought that logic's distinctively formal. So it's somehow in virtue of the shape or structural patterns that arguments instantiate that explains their validity or invalidity. And if we look at Aristotle in prior analytics, we see that it's both. I think clearly both thoughts are going on in his writings. If we look at medieval logicians, they seem to think that logic was distinctively modal and not formal, so they're very keen on capturing arguments like a person runs, therefore an animal runs, that sort of thing, which normally we wouldn't think is valid, doesn't look formally valid, but they think it's got this modal component, it's necessarily truth-preserving, and therefore should properly be considered part of logic. More recent authors like Tarski, Bolzano, and Quine, I think, treat consequences purely formal, and the modality drops away. And we'll, in one way or another, fairly suspicious of modal ideas and give definitions of consequence that are purely formal. And then for others, so people like Bertrand Russell, or at least certain time slices of Bertrand Russell, it seemed that logical consequence is neither modal nor formal, it's just material truth preservation, it's just given by the material conditional, or what we sometimes call Philonian consequence. So I think Tim Smiley's exactly right that there's this tangle of ideas going on, and it's not obvious that we can respect all of those. So if we're going to give an account of validity or of logical consequence, I think what we need to do is take one strand from this sort of picture, or some consistent subset of these thoughts anyway, and precissify it up into the sort of thing that we can hope to model and capture formally. So that's what we're going to do today. And the thought that we're going to go with is the idea that logic is distinctively formal. So we're going to try and give an account of consequence which is purely formal, doesn't make any appeal to modalities or any of that nasty business, just done in terms of nice tidy forms. So what do we mean when we say that logic is distinctively formal? Well, I think the first thought we might have is something like this, that logic's concerned with inference patterns or forms in something like the following way. Valid arguments have forms expressed by schemata, all of whose instances are valid. So a very straightforward example, something like P and Q, therefore P. Why is that valid? Well, that's got a form expressed by A and B, therefore A, and all of the instances of that form are truth-preserving. As long as we insist that the variables are replaced uniformly and those sorts of constraints are in place. Why is that valid? It's valid because it's got that sort of form, and every instance of that form is a good instance. It's never going to take you from truth to falsity. So that's the first sort of idea we might have. And I think that's the idea that Tarski starts out with in his 1936 paper. So this is the famous paper where he defines logical consequence model theoretically. This idea of logic as distinctively formal is clearly in the background, but he notes that it must be incomplete. Because underlying the whole construction is the division of the language discussed into logical and extra-logical. The division is certainly not quite arbitrary. If, for example, we're to include among the extra-logical signs the implication sign or the universal quantifier, then the definition of the concept of consequence would lead to results which obviously contradict ordinary usage. So all well and good saying that logic's distinctively formal, valid arguments have these well-behaved forms, but to understand what the form of an argument is, we need to have first divided the language into the logical and the extra-logical. We need to have given some sort of account of what the logical vocabulary is, or what we're going to call the logical constants. And Tarski goes a bit further. He starts thinking about, well, what might it be that's distinctive about the logical vocabulary? How might we start to distinguish what's logical? And he says this. So this is in a slightly later paper. He talks about the logical constants as terms of a much more general character occurring in most statements of arithmetic, terms which are met constantly both in considerations of everyday life and in every field of science. So the idea here, and I think elsewhere in Tarski's writing, seems to be something like this. The logical constants are distinguished by their generality or their topic neutrality. They don't have any particular subject matter themselves, they're not about anything, but they're the sorts of expressions that you're going to need if you're going to carry out inference, and that apply to any domain of reasoning whatsoever. If you're going to be carrying out correct inference, you're going to need these things. They have this peculiarly general topic-neutral character to them. They don't have any particular subject matter themselves. And I think that seems quite appealing, and John MacFarlane, following up on this kind of thought, cashes out this idea of topic neutrality further as indifference to the particular characteristics of objects. So his thought is, well, if you've got an expression which behaves exactly the same way when you're reasoning in any domain you like, and however the things in that domain are arranged, then that expression has a good claim to being topic neutral. Because you were reasoning about these things, but you just as well have been reasoning about anything, and it would behave the same way. So expressions that behave exactly the same, we're going to make this idea more precise, but expressions that behave exactly the same way over any domain, those look like they've got a decent claim to being indifferent to the particular characteristics of objects, indifferent to the particular qualities of whatever we're talking about, topic neutral. And finally, Tarski's suggestion for making this idea even more precise is to put forward a test of isomorphism invariance. So in a much later paper, one of the logical notions, Tarski thinks that isomorphism invariance is a really nice way of capturing this idea of topic neutrality. And here's what he says. What would be the science which deals with the notions invariant under the widest class of transformations? Here we'll have very few notions, all of a very general character. I suggest that they are the logical notions, that we call a notion logical if it's invariant under all possible one-to-one transformations of the world onto itself. So this idea of topic neutrality has now been tidied up in terms of indifference to the particular identities of objects, and we've got isomorphism invariance now coming in as a test for whether a particular expression is topic neutral is indifferent in the sense that we're looking for. Okay. So just summing up where we've got to so far in terms of what we mean when we say that logic is formal, before I give you a statement of the isomorphism invariance account, idea is this. Logic's formal. That's got as good a claim to being the characteristic feature of logic as anything has. That's the one we're running with, given that there's this messy history and we can't possibly capture everything. What does it mean to say logic's formal? Well, it's schematic. Valid arguments have these forms, all of whose instances are truth-preserving, but that needs an account of the logical constants. What are the logical constants? They're the topic neutral items. They're indifferent to the characteristics of objects, and an isomorphism invariance test is going to be a nice explication of that idea. Okay, so now let's go through the account itself. Now that we've given it some philosophical motivation from the thought that logic is distinctively formal. So let's start with a little baby example. So this is going to be familiar to a lot of people, but we're going to say that a permutation is a bijection from a set onto itself. So in a real toy example like this, we've got the numbers 1 through to 5. So we're taking that set of numbers, and then we are mapping those numbers onto themselves, onto that set. And we're doing it in the following way. So 1 gets mapped to 1, 2 gets mapped to 4, 3 to 5, 4 to 3, and 5 to 2. So that's just a way of bijecting, or if you like, rearranging the things that are in that set, the set of the numbers 1 to 5. Now once we've permuted the set in that way, we can talk about things being invariant or variant under that transformation. So on this particular permutation, which we're calling pi, 1 is invariant, because 1 got mapped to itself. So it's the same after the permuting as it was before. All the other numbers, 2, 3, 4, and 5, those aren't, because each of those got mapped to something different. The singleton of 1 here, that set is invariant under this transformation because all the members of that set got mapped to themselves, in particular just 1, which got mapped to itself. But for example, the set containing the numbers 1, 2, and 3, that's not, because that's being mapped to the set containing the numbers 1, 4, and 5, and those are different sets. So that's variant, although the singleton of 1 here was invariant. And finally, the ordered pair of 1 and 1, that of course is going to be invariant, again because its members taken in order are mapped to themselves, so you end up with exactly the same pair, 1 and 1, but this triple here, 2, 3, and 4, that's not, because that got mapped to 4, 5, 3, which is not the same triple. So just a very basic introduction to what the idea of a permutation is that we're going to be working with. Yeah.
So will it matter when you, I suppose when you're looking at a product set, so you have ordered pairs.
Yeah.
You're always doing permutation inside the individuals and never mapping them to. So it's not an arbitrary bijection on the product space. It's being induced by a mapping on the underlying space.
Yeah. So everything that's said so far, yes. Yeah. Although we're going to generalize the idea a little bit. But yeah. Okay, so now, here we go. Here's a brief statement of what we're going to mean by isomorphism and variance. Everything I've said so far has been about numbers or sets, or generally stuff in the world. But of course, stuff in the world isn't the sort of thing that we think is a logical constant. Logical constants are bits of language. So we need to tie this now from stuff in the world into bits of language. And we'll say, let sigma be an expression. So just some item in our vocabulary. Now, in exactly the usual way, let's say that sigma d is the interpretation of that expression on a set of elements d. So that's just what we're mapping sigma to on a particular interpretation. That's what it picks out. Now, suppose that for any set d and any bijection pi on d, the original interpretation is identical to the permuted interpretation. So the thing that our permutation mapped the original entity to. Well, if it is, on any bijection, then that expression we're saying is isomorphism invariant. So isomorphism invariance is getting understood first for the worldly entities, which are the sorts of things that we think our logical constants pick out, and then derivatively for bits of language, where something's going to come out as isomorphism invariant if its interpretation is. That's the idea. And here we're generalising the idea to any bijection pi of d, because of course we don't think there's anything special about the baby interpretation we just went through, just mapping them as one five to themselves. To pass this test for isomorphism invariance, you have to be invariant under any bijection of the domain. So this will be best understood with some examples. So let's go through a couple of examples. First of all, let's think about something that fails the test. So think about some domain D that contains some red stuff and some green stuff. Let RD be the set of red things, and now let pi be a bijection that swaps a red thing for a green thing. Okay? Well, then there's going to be some red thing, A, which was in the extension of red things, and permutation pi of that thing, which is not in the original extension, because we mapped a red thing to a green thing. So the original interpretation, this thing here, intuitively the set of red things, is not identical to its permutation because we swapped a red thing for a green thing. So what does that show? Well, that shows that the predicate is red is going to fail to be isomorphism invariant. And so it's going to fail to be a logical item of vocabulary. And that's of course what we want. We don't normally think that a predicate like is red is a distinctively logical notion. And it doesn't come out as logical on this account. So that's nice. So that's an example of something failing the test. Let's have an example of something passing the test. And I think the most obvious candidate here is the identity predicate. So here, take any domain of objects you like. The identity relation is going to hold between each object and itself and nothing else. And then however you play around with that domain, however you transform it, everything is still going to be identical to itself and nothing else. So the extension of the identity predicate is going to stay exactly the same, so identity comes out as logical. And again, that's usually what we want. There's a little bit of controversy about whether identity is a logical constant. It comes out as logical on this account. I think that's at least the mainstream view. Now, Van McGee in a paper Logical Operation shows that you can extend this account to the sentential connectives, and all of the usual conjunction and disjunction and material conditional, those all come out as logical. The details there are a little bit messy. I'm happy to talk about it during questions. I'm going to skip over that now, because really all that matters for this talk are the quantifiers. So we're now going to move on to think about quantifiers, and that's where the overgeneration argument is going to get in, if it gets in at all. So we're going to skip over the other sentential connectives. Just now, take it from me, but you can do it. Okay, so quantifiers. Well, the usual first order quantifiers pass the test, and I think intuitively it's fairly easy to see why that would be the case. Intuitively, take some domain of objects, and if everything in there is f, then however you commute it, everything in there is still f. So, very intuitively, that's why the universal quantifier passes the test. Existential quantifier, take any domain of objects, if something in there is f, then however you commute it, something is still f. So the existential quantifier passes. The problem is that an awful lot of other quantifiers pass as well. So we get the nice first order quantifiers that we all know and love, but we also get these things coming out as isomorphism invariant and so logical. So first of all, this one, the first quantifier I've got there is true in a model just if the domain is an uncountable set. The second is true in a model just if there are Aleph n objects in the domain for any value of n that you like. Now, why would that be a problem? Well, you might think, if these are passing the test, and again, it's fairly obvious to see why they pass the test, because these are quantifiers that are measuring size in some way. First talking about uncountability, second talking about particular sizes, and generally speaking, if the domain is a certain size, then however you commute it, it's still that size. So these things which are distinctively about the size, the cardinality of the set, those are all going to come out as logical on this approach. And if you worry about this, then you're going to think, well, hang on, these ideas here, like ideas of uncountability, those aren't logical ideas. We're now in the realms squarely of doing maths at this point. This isn't logic. This isn't topic neutral. if we're talking about uncountability, then we're really in the realms of doing set theory. And set theory is not topic neutral, it's about sets. That's the sort of worry that you might have. I think that's the worry that the people putting forward the overgeneration argument have in mind. So now let's think about overgeneration in a little bit more detail. So again, roughly the idea is this. On the isomorphism invariance account, motivated by this idea that logic is formal, we get all of the usual stuff that we like coming out as logical. So it doesn't look like we've got an undergeneration problem. We get the usual quantifiers, we get the sentential connectives, and we rule out lots of the stuff that doesn't look very logical, like is red. But nevertheless, we might be too generous, we might have let in too much as logical, in particular these things about cardinality. So now let's get this worry, this overgeneration worry, slightly more precise in order to make our response. So the two main authors, there's a lot of people that have criticised this account of the logical constants for overgeneration reasons. The two main ones I'm going to look at are Feferman and Bonnay. And here's what they say about this. So Bonnay says that this treatment of the quantifiers suggests that Tarski's criterion overgenerates and counts too many operations as logical. First, since the aim is to distinguish the realm of logic proper, a proposal which conflates logical notions and mathematical notions does not seem to be on the right track. He writes that the account yields a collapse of logic into mathematics. And Feferman writes that the account assimilates logic to mathematics, more specifically to set theory. So the idea clearly is we've gone too far, we've let through mathematics, logic has ended up being too close to mathematics on this picture, in a way that we shouldn't want if we were motivated by topic neutrality.
Is that because mathematics is taken to not be topic neutral?
Yeah. Yeah, just because if you're doing arithmetic, it's got subject matter, it's about numbers, set theory is about sets, those have.
So this is like
subject matters.
Okay. Some Platonist perspective about number or something like that.
Yeah, well, I don't know if it. I mean, certainly that would be such a candidate. I don't know if you have to be Platonist about it, but you just.
To me, numbers apply to almost everything, you know.
Sure. Well, I mean, in that case, you're not going to worry about the overgeneration argument in the first place, so that's kind of okay. So this is just to try and reassure people who do have this concern that we want logic mathematics to be seen. Okay, now when we look for more precise arguments in the literature for the overgeneration claim, we find that the same example always comes up, and that's the example of the continuum hypothesis. So again, taking Feferman and Bonnay as our main characters here, we can express the continuum hypothesis and many other substantial mathematical propositions as logically determinate sentences. Feferman and Bonnay, the quantified Q Lf1, which tests whether they're exactly Lf1 objects satisfying the formula, is logical. Intuitively, something's gone wrong. Being of size, Lf1 is a notion that belongs to set theory, not logic. Okay. So, here's the continuum hypothesis. Now, it really doesn't matter that we've gone with the continuum hypothesis example here. There are lots of set-theoretic examples that would work. Really, all that's important is that thing at the top there, the continuum hypothesis, which says roughly that there's no size of infinity between the infinity of the natural numbers and the real numbers. That's definitely maths. So we could plug in lots of different things for CH there, but that's just a mathematical claim. We're meant to agree on that. Now, how do we get from that to a problem for isomorphism invariance? Well, we need to cook up a sentence like S here. Now, S says roughly the following thing. So that's a sentence of second order logic, and it says very roughly, take any x, y, and z. If x has the size of the natural numbers, and y the size of the real numbers, and x is smaller than z, then y is smaller than or equal to z. Now, all of those seemingly non-logical expressions there, your n, your r, your less than or equal to, those can all be defined away in purely second order terms. So this is a sentence of pure second order logic. It contains only the logical constants of second order logic. I use the shorthand because if I didn't, it would be enormously long and difficult to deal with. again, the details don't matter terribly here. It just needs to be some sentence of pure logic, just using logical constants, which is, in a sense, sensitive to a mathematical claim like the continuum hypothesis. So all that really matters is, and I'm going to say a lot more about this, that CH looks mathematical, S looks kind of logical. That's really all that matters for now. And yet we find that this is the situation. S is logically true if and only if the continuum hypothesis is true. So we have this relationship now between the logical truth of a sentence and the plain truth of a mathematical sentence. And it turns out we can cook up a distinct sentence, S primed, that's logically true just if the continuum hypothesis is false. Let's just assume for today that it's true. We could run exactly the same argument for its on the assumption that CH is false. Let's just say for today that it's true. Now, how do we tie this up to isomorphism invariance? Well, every expression that's involved in S there is isomorphism invariant. Every expression in it passes this test. So that sentence S is coming out as a logical truth if you buy isomorphism invariance, and yet it looks quite closely related to a mathematical sentence. So that's the observation that's meant to get us to some sort of problem for isomorphism invariance. Okay. So what I'm going to do now for the remainder of the talk is go through 4 attempts at getting from this observation about the relationship between CH and S to some sort of conclusion of the form isomorphism invariance is rubbish. What I'm doing is doing quite a lot of work on behalf of our opponents, because Feferman and Bonnay and other people writing on this don't go into very much detail about how this argument's meant to go, but we're going to go through 4 of them. So I keep saying we because, and I should have said this at the beginning, this is all joint work with Alex Paseau at Oxford. So, okay. Here are the 4 versions of the argument that we're going to go through. These are the 4 problematic conclusions that we might get to. First, isomorphism invariance renders logic sensitive to mathematics in a problematic way. We'll say a lot more about what we mean by sensitive, but that's the first general thought. Second, it renders the continuum hypothesis logically true or false. So if you buy into isomorphism invariance, you don't just have to buy the truth of the continuum hypothesis or its falsity, you have to buy into its logical truth, and that might worry you. Third, maybe it somehow epistemically determines the continuum hypothesis, so it gives us some new epistemic route to knowledge of the continuum hypothesis, which logic shouldn't do. Fourth, it lets the continuum hypothesis be logically expressible, so it allows us to somehow express the continuum hypothesis in purely logical terms. So for the remainder of the talk, we're going to go through these 4 potentially problematic claims for the proponent of isomorphism invariance. So let's start with the first one. Oh, first of all, before we go through those, let's just point out a few features of these sentences CH and S, which are going to be helpful and which we're going to be returning to at certain points during these arguments. So the continuum hypothesis, as I've said, that's meant to strike us as a mathematical sentence. Looks pretty plausible. It's not topic neutral, because it's about sets, sizes of sets and relationships between them. And 3, it's existentially committing. Right? If it's true, then on a face value reading anyway, it's an identity claim, identity statements get flanked by singular terms, those are names for particular mathematical objects. So it looks like its truth relies on the existence of some mathematical objects. S, on the other hand, doesn't obviously look like a mathematical sentence. As I say, it contains only the pure vocabulary of second-order logic. It looks pretty topic neutral. All of the expressions in it pass the isomorphism invariance test. That was our test for topic neutrality. And it looks existentially innocent. You know, unlike the continuum hypothesis, there's no existential claim going on there. The overall shape is just a conditional with some leading qualifiers. Yeah?
Just a clarificatory question. This is from someone who didn't take math past the first year in university. And that was a long time ago. But why is S not a mathematical sentence? Because it contains the mathematical notions of the real numbers, for example.
Yeah. So S only contains isomorphism and invariant vocabulary, and it only contains the logical constants of second order logic. So it does, on the face of it, look like it says something about the natural numbers, something about the real numbers.
Yeah.
But those aren't just there for shorthand. Those can just be, all of those defined away using quantifiers and all the usual logical apparatus. So S is just a shorthand for a massively long thing that only contains quantifiers, conjunctions, disjunctions, and conditionals.
Okay, thank you.
What is the less than? I wish I understood. I don't really understand the sentence. What is it interesting?
Well, it's just the idea of a set being smaller than another one is something that you can, in a sense, so we're going to get onto this, express in a long second order sentence. So it's the, maybe we can talk about that a bit later, but for now, I mean, if you want to see how something like Shapiro's book on second order logic goes through all of these definitions.
I trust you, yeah.
Yes. Okay. So here are the arguments. Let's start with the first one. So the first one was saying this: isomorphism invariance renders logic sensitive to mathematics, and that's bad. Now, what might we mean here? Well, if this is the worry that you put forward, it looks like you think something like this. The extension of the concept of logical truth varies with the truth value of mathematical sentences. You know, continuum hypothesis is either true or false, you might think. If it's true, then S is a logical truth. If it's false, S isn't a logical truth. So there's some sort of sensitivity there between the truth value of mathematical claims and the extension of logical truth. And you might think that's bad. Logic should just be independent of mathematics and shouldn't be hostage to it in this kind of way. Now, the next three arguments that we can go through, I'm going to try in each case and knock down. This one we just have to accept and say, look, these are true, those conditionals are true. So we do have that minimal level of sensitivity between logic and maths on the isomorphism invariance approach. So the best we can do is to try and say that that's nothing scary. In fact, that's nothing terribly unfamiliar. And here's an analogy. So take a really simple arithmetic case, like our sentence A here, 2 plus 5 equals 7. So again, a claim of maths, much less controversial than the previous claim we were looking at, the continuum hypothesis, but nevertheless a claim of maths, an arithmetic claim. Well, it looks like you're going to be able to cook up first order sentences which are analogous to A in something like the way that S is related to the continuum hypothesis. So this sentence here, A prime, what does that say? Well, that says if there are exactly 2 F's and exactly 5 G's, and nothing's both F and G, then there are exactly 7 things which are F or G. Now again, on the face of it, you might think, well, that looks like there's some mathematical stuff getting involved, but again, that's just shorthand. The existential quantifiers subscripted with numbers there, those can all be defined away in the normal sort of way. Now, our claim is that the continuum hypothesis, well, like the continuum hypothesis, A there is a mathematical claim. It's not topic neutral, it's about numbers. It's existentially committing, for the same reasons the continuum hypothesis was. It appears to talk about, there appear to be some names there, and there's describing some objects and relations between them, and therefore not logical. So you have to think that if there's to be any problem there. Like S, our previous logical claim, A primed there looks like it's not mathematical. That's expressed just in the language of first order logic. It appears to be topic neutral. All of the expressions there pass the isomorphism invariance test, and it looks like you really could be reasoning about anything there when you're deploying something like A primed. It's existentially innocent. Again, it's just the overall shape of things are conditional. There's no existential implications of that, and so we claim logical. So the situation then between the continuum hypothesis and that sentence S that we cooked up, we think is analogous to the situation here between our arithmetic claim A and the logical sentence related to it, A primed. S is logically true just if the continuum hypothesis is true. A primed is logically true just if A is true. So we seem to have that sensitivity even in the much more familiar first order case. that everyone seems to be happy with. Certainly our opponents in this debate seem to be happy with. Feferman and Bonnay, people like that, they argue against the isomorphism invariance approach. They give alternative characterizations of the logical constants, and all the first order constants past that. So we say what's going on in the first order case is just analogous to what's going on in the second order case. We're not normally bothered by the first one, we shouldn't be bothered by the second one. So yes, we do have this sensitivity, but we always have that sensitivity, and that's nothing surprising, there's nothing to be scared of. Here's the second argument. So here now we're trying to establish the claim that isomorphism invariance makes the continuum hypothesis logically true, if true. So a different conclusion to the first one, and one that we admit would be problematic. If we think that logic should be topic neutral, and we don't think that the continuum hypothesis is topic neutral, then we don't want that coming out as a logical truth, if it's true. So I'm going to think about two ways that we might worry about the continuum hypothesis coming out as logically true on this account. So first of all, maybe here's what you think. Well, a sentence is logically true when its formalization is logically true. That sounds pretty good. That's the sort of thing we teach our students. And, of course, the continuum hypothesis here is a claim in a technical fragment of natural language. Whereas S, that was a sentence of logic. S is going to be logically true if the continuum hypothesis is true. So if S is the formalization of the continuum hypothesis, we might think the continuum hypothesis is logically true. That's the way this worry might go. Now, to that our response is this. S is not formalization of the continuum hypothesis. Obviously there's some relation between the two, there's this sort of sensitivity going on, but it's not a formalization. There are the sentences again. What would a formalization of the continuum hypothesis be? Well, the standard way of formalizing continuum hypothesis is as a really long first order sentence in the language of set theory with set membership as your single non-logical expression. That's what we normally give as a formalization of the continuum hypothesis. And that, of course, is not S. In fact, you might think that S is a really bad formalization of the continuum hypothesis. I mean, apart from anything else, we've gone radically against the surface grammar of what we started with, as meant to look like an identity claim holding between two names. We've now turned it into this thing, which includes all of this logical vocabulary. Doesn't look like a very good candidate for a formalization of the continuum hypothesis. And again, I think to make this point more precise, think about the relationship between A and A prime, the more familiar case. We don't normally think of A prime as a formalization of A. If we're going to formalize something arithmetic like A, we normally go for something like this on the bottom line here. There's the addition sign, that's some sort of functional expression. It's holding between two names, A and B. Then we've got an identity sign, then we've got another name, C. That looks like the shape of that thing. It looks like if we were going to formalize it, we would end up with something like this, not something like this, which again looks radically different where we started. So you'd at least need to do an awful lot of work to convince me that S was a formalization of the continuum hypothesis. On the face of it, it really doesn't look like much of a formalization at all. So I suggest there's not much hope for an argument running this kind of way to the conclusion that the continuum hypothesis is logically true. But maybe you don't have that in mind as your argument here. Maybe you think something like the following. Well, rather than worrying about formalization, we're going to think about the behavior of the operator, it is a logical truth that. And maybe you want to argue something like the following. It's a logical truth that S is true if and only if the continuum hypothesis is true. Therefore, 3, it's a logical truth that the continuum hypothesis is true. Logical truth that CH. Maybe you want to run something like that sort of argument. Problem here is, let's assume that the correct logic to treat this it's a logical truth that operator is S5, modal logic S5. That's usually taken to be the logic of logical necessity. Let's say it's S5. The problem is this is going to be an S5 fallacy. The argument from 1 and 2 to 3 is not going to be a valid argument of S5. What would be a valid argument is if we removed 2 and replaced it with that. It's a logical truth that S if and only if CH. Then 1 along with that really would get you to the bad conclusion that the continuum hypothesis is a logical truth. But we need an argument for 2 primed for that claim being a logical truth, which is at least far from obvious. And I think worse still for our opponents here, that sort of strategy is going to prove too much. Because if you think that about this case with CH, it seems like you'd have to say the same in the first order case between the arithmetic claim A and A primed. And if you endorsed a principle like 2 primed, the conclusion that would get you to is that 2 plus 5 equals 7 is logically true. Now, saying that 2 plus 5 equals 7 is logically true, that's the sort of thing that we'd associate with logicism. I don't think logicism is true. I think that there are very well-known problems with logicism. Moreover, in this context, it's rejected by at least one of our opponents here, Feferman. So I don't think this is a very attractive route to creating a problem for isomorphism invariance either. Okay, let's have a look at the third one, and then for time we may finish there, and I'll gloss over the fourth. So forget all that, and now we're thinking about a different argument. And this is an argument to the conclusion that the continuum hypothesis somehow gets epistemically determined if we accept isomorphism invariance. So some sort of new route to knowledge of the continuum hypothesis is opened up if we accept this view. That would be the worry. But again, let's think about 2 ways that we might try and reach this problematic conclusion. And the first considers the behaviour of the operator, it is an a priori truth that, as opposed to it's a logical truth that. Now, this argument here, it's an a priori truth that S, it's an a priori truth that S if and only if CH, therefore it's an a priori truth that CH. Unlike the modal argument before, that looks like a sound argument to me, assuming that you can distribute a priority in that way. But let's allow that. Well, I don't think that can quite be the problematic conclusion that you have in mind here, because of course what this is going to give us is that the continuum hypothesis is a priori knowable. And presumably that's not a problem, because it looks like we don't know the value of the continuum hypothesis, but when we do have some route to knowledge of the continuum hypothesis, that's going to be a priori. So I think the idea that the problem would be the continuum hypothesis being a priori knowable can't really be the worry that people have in mind when they're thinking about this. Rather, I think the worry is something like the following. And I'm thinking specifically of Feferman here. Feferman seems to think that if we accept isomorphism invariance, we're going to somehow bring about knowledge either of the continuum hypothesis or of its negation. And then perhaps we've got some worry like the following one: logic alone shouldn't force us to accept or deny controversial claims of set theory. Again, if you think that logic is distinctively topic neutral, then that looks quite attractive. It shouldn't force us to accept or deny controversial claims of set theory. But I don't think it does. And that's because we're denying that if we accept isomorphism invariance, there's some new and problematic epistemic route to knowledge of the continuum hypothesis or its negation. And the reason for that is, remember that there's another sentence out there, S primed, that I flagged at the beginning. So that's going to be the sentence that's logically true just if the continuum hypothesis is false. So S is logically true just if the continuum hypothesis is true. S primed is logically true just if the continuum hypothesis is false. S prime also contains only isomorphism invariant vocabulary, only logical constants of second order logic. What that shows is that isomorphism invariance is compatible with both the truth of the continuum hypothesis and the falsity of it. Right? It doesn't force us one way or the other. It turns out that if the continuum hypothesis is true, then this is a logical truth. If it's false, then this other thing is a logical truth. But it's totally compatible with both. It doesn't force any truth value of the continuum hypothesis upon us. It doesn't form any new route to knowledge of the continuum hypothesis. So in short, isomorphism invariance alone can't deliver the truth, the logical truth of S. Isomorphism invariance and the truth value of the continuum hypothesis would. So the expected order of discovery would be this. You like isomorphism invariance, you think that's the right account of logical nature. You then discover that the continuum hypothesis is true, and you conclude that S is a logical truth. Or alternatively, you discover that the continuum hypothesis is false, and you conclude that S prime is a logical truth. But it's going to be isomorphism invariance and the truth value of CH that does the work here, given that isomorphism invariance is compatible with both. So it's not going to force CH or not CH on you. Okay, well the fourth one here is just one slide, so let's quickly go through this and then we can have some questions. Final argument. Bonnay writes that on the isomorphism invariance approach, it's possible to express the continuum hypothesis in isomorphism invariant vocabulary. So the idea is that there's some sort of worry that you shouldn't be able to express mathematical claims in purely logical terms. That's something like that seems to be doing the work here. Now here I think the response for the fan of isomorphism invariance is just dig their heels in. What's expressible, we've seen, in isomorphism invariant terms is not CH, it's the sentence S. Now, no one thinks the expressibility of S is problematic, because of course if we're right that its logical truth is unproblematic, then of course its expressibility is, because if it's a logical truth, it's got to be expressible. I think the worry here is that you might casually say something like, CH and S express the same thought, they say the same thing, they have the same content. That's the sort of thing that you can imagine a mathematician saying. These two sentences, they just say the same thing, CH and S. And I think in certain contexts, that claim is totally innocuous. Similarly, between our arithmetic claim A and A prime, the claim that they say the same thing is absolutely fine sometimes. But the problem here is that in this context, what we're doing is trying to demarcate logic from mathematics. That's the context that we're in, trying to find out where the line is between logic and maths. So when this is the game, those are exactly the sorts of illusions you really don't want to make. It's really dangerous in this context to start talking like that and saying that CH and S say the same thing. This is exactly the place where we need to speak very carefully. And when we speak very carefully, we won't say that the continuum hypothesis is expressible in isomorphism invariant terms. We'll say that S is. And I think that's really crucial for this discussion. Fine if you want to go making those sorts of claims in the pub about CH and S. But here, I think we need to be really careful. That's a pub, but here we need to be really careful to keep these things separate. Okay, so summing up, where have we got to? We've said that isomorphism invariance has been charged with overgenerating. We then considered 5 possible, but we didn't, we considered 4, I removed one this morning. We considered 4 possible claims that might be happening, 4 possible problematic conclusions that we can get to when we consider isomorphism invariance and the continuum hypothesis. Those are the 4, that it renders logic sensitive to maths, that it makes continuum hypothesis logically true, it epistemically determines it, it makes it expressible. We said the first one is fine. There is that minimum level of sensitivity, but you can sleep easily. We already had that in the first order case. 2, 3, and 4 we think all fail. We considered a couple of ways of trying to get to the conclusion that CH is logically true, argue that those fail. A couple of ways to create an epistemic problem here, saw those to fail, and then for the expressibility point we dug our heels in. Now, isomorphism invariance of course might still fail, but the claim here is just it doesn't fail for this reason of conflating logic and mathematics. So I think it remains a really attractive account of logical nature. We certainly need such an account if we're going to complement the usual model-theoretic definition of logical consequence. And I think that this one is philosophically motivated by the thought that logic is formal. It at least doesn't look like it undergenerates. It can be given precise set-theoretic expression, and I've argued here today that it doesn't overgenerate either. So I'll finish there.